Okay, let's start. Welcome back. And today we're gonna learn something more about nice tools you can use to get more information out of text. So still no deep learning this, but we will come to this very soon. So I just told it to the people who were here a little bit too early. We're gonna work with 3 very powerful libraries in Python to get more information out of text. And these 3 libraries are really hard to install if something goes wrong. So it's always a problem when you're working with Python 3 or Python 2 and everything can go wrong. I'm talking about pattern, the library pattern, and the library spacey. And for the NLTK library, we're going to use some advanced models that have to be downloaded separately. So we'll come to this at a certain point. But I think all 3 Jupyter notebooks I put on Moodle are already run. They are saved in a status where all the outputs are already shown. So even if it doesn't work with you to install all the libraries right now, you still can just have a look at all the outputs and see what's happening here. So first thing we want to introduce is part of speech tagging. We talked last session about computer vision and why deep learning is so powerful in computer vision. And one point is that in computer vision you have these different layers of the images. So for example, you have 3 channels for different colors. There might even be more channels, and therefore you have a multi-dimensional tensor that is used as an input. It's not just a big table where every pixel is one data point, but it's really a multi-dimensional tensor. And in computer vision we found out, not we, but the guys from computer vision found out that deep learning algorithms are very powerful when you are working with these multi-dimensional tensors. So it would be quite nice if you could have something similar to this, not for pictures or videos, but for text. So if we could construct an additional layer of our text, this might work very well with the algorithms we want to use later on. And the next point is we could give some useful information about the text. Because when we are looking at a text, as a human, we already know directly, oh, this is, for example, a noun, this is a verb, and so on and so on. But as you may know, or as you definitely know when you think about it, there are many words that could be nouns and verbs, for example, or it's not clear, is this an adjective, or is it a name, or whatever. If you could give this additional information to the computer, this might increase the ability of the computer to understand what is really going on in the text enormously. And the first thing that could be done is part of speech tagging. And here, as an example, I just used the first sentence of the Wikipedia article about artificial intelligence. So the whole sentence is, artificial intelligence, sometimes called machine intelligence, is intelligence demonstrated by machines in contrast to natural intelligence demonstrated by humans and other animals. And first things we do is we just tokenize this text. We use the NLTK word tokenizer that we used in the previous section. And now we add something. We take from our tokens the so-called POS-Tag, so the part of speech text, and let's see what happens. Oh, I was in the wrong line. Sorry for this. Here. So what we have now is we have our sentence. The sentence still is a list, so it's a tokenized sentence already. But now every element in the list is not just the token, the word, but it's a tuple. And for each word, we have an additional information. For example, artificial is an adjective, called is a verb, and so on. So this is exactly what we want. Very cool. Of course, there are different libraries that can do the same, but slightly different. And one very powerful library, as already mentioned, is Pattern. And if you get it installed, and it works very, very nice. And we will do a third Jupyter notebook today only on Pattern, because I think Pattern is one of the strongest tools that you can use. You can do so much with this library, but the documentation is very, very bad, so no one really knows what you can do with it. So I made a little notebook just to give you some ideas what Pattern really can do. But here you see it's more or less the same, but these codes are different. So you need a list. What does it really mean? Or perhaps even not. For machine learning, let the computer learn what it really means. It doesn't matter. But in principle, it's really the same thing. So this is the first level where we can get additional information about our text, part of speech tagging. But there is more we can do. We started from big texts and then tokenized the text into sentences, and then directly tokenized the sentences into words. But perhaps this is not the only way to do it, and sometimes it might not be the best way, because the words, the combination of words, and shorter parts of the sentences, so-called chunks, may be very important. Pattern is able to do chunking, and then it looks like this. So in our, still we got a list, and we have a sentence is the first element in the list, and in the sentence now we have tuples where we have additional information. So we have artificial, this is our part of speech tagging, but we have additional things here. This, for example, means artificial is part of a noun phrase, NP. We're going to see some better visualizations of this, but we even got relations, which parts of the sentence belong to which other parts. So let's have a look at the chunks. This was our sentence tree list, and now we can just loop over the list and print all the chunks. So we get an element for every element in the list that is already called chunk from the pattern library. And now we got the chunks, and we see artificial intelligence is one chunk. AI, this is what was in the brackets, sometimes called as one chunk. Machine intelligence, here. In contrast to the natural intelligence displayed by humans and other animals. So you see, it makes a lot of sense to chunk the sentences if you want to have a higher level of representation. So for example, artificial taken as one word could mean more or less everything. It could be an artificial building, or the adjective could just mean that something is artificial in the way that it was made up and not the way it normally should be. But if you have the chunk artificial intelligence, this makes a lot more sense for us as humans, and it might make more sense for the machine in the end as well. Because then, for example, if you could train a machine learning algorithm on chunks and not on single words, you always get a better understanding of the context. One approach that is used in machine learning for understanding text, I think I already discussed this last session, is the back of word approach. So you just take every single word and don't look for the order of the words in the document or in the sentences or whatever your level is, but you just have every single word and just count the number of appearances of this word in this document, text, or whatever, and you can do a lot of things with this. One more advanced approach is to combine so-called n-grams. Normally, for example, bigrams. So you're taking two words. In our sentence, you would take artificial intelligence, first bigram, and then intelligence, AI, a second bigram. So you have a moving average window that is going over the text, and you can have bigrams or trigrams or whatever. But then you get a lot of combinations of words that is not really so meaningful. Because then some words are combined with other words just because the next word is the next word and not because there's inner logic. Instead of using bigrams, it might be a very good approach to chunk all your data and take the chunks and then run a normal back of word approach on the chunks. So this would mean in our back of word we wouldn't have the word artificial nor the word intelligence, but we would just have the word or the chunk artificial intelligence. This would work quite well. Of course you can combine it, you can make a bag of word with every single word and then add just as additional variables the chunks, for example.
I have one question back to the tagging that we did before. So how does the machine now differentiate between text as a noun and a verb? We haven't really, so how does NLP solve this problem?
There are different approaches how to do it.
Yeah.
One is just to learn the words, and then there might be misunderstanding of it. The models that are applied here are already trained machine learning models. So they're the linguists at Stanford, they have labeled a lot of sentences and seen what is a verb, what is an adjective, and so on and so on and so on. And this information was used to train your own POS-Tagger. In this book, you find examples how to build your own POS-Tagger if you want. So it's not so difficult in the end.
And which rules did they apply when, so coming now to the parse tree, or to the chunks, so which rules did they apply in order to label the chunks in the sentences, because this is machine learning too, right?
Yeah, of course. But I cannot tell you how it exactly works. You would have to look at the documentation, and probably don't find the answer in the documentation, because this is pattern, and pattern is really, really bad document. But it's something that works quite well.
Yeah.
So later, in the end of the seminar, we will use real deep learning algorithms to do something that is normally called text summarization. So you have a long text and you want to identify a shorter version of this text. And this is an approach that could be used for chunking as well. So now we just printed the chunks in a more nicely, and but it's the same. But now you got the information. So we have a noun phrase, and the noun phrase is artificial intelligence. Another noun phrase, AI. A verb phrase, sometimes called. So a phrase, a chunk in which a verb appears, is identified as a verb phrase. And we have propositions, for example. By, in, by. And these are things that you can use as well if you want to, for example, if you would like to build a knowledge graph out of text, which is something that is very state of the art in natural language understanding. So you're trying to build a knowledge graph, get the information of the text. Then it might be very interesting to see the propositions. So how is one chunk combined with another chunk? Does it tell us something about the place, or does it tell us something about the time? And questions like this. But it's this information might not be so interesting if you really want to go into machine learning, deep learning. So these functions are just functions to visualize the output in a more appealing way. Because if you don't do it, you still got this sentence here, everything is put together, but now we're going to use the function. So these are just different print functions that you can use to see what is the information I'm interested in right now. So it depends if you want to see all the elements in the lists or if you don't want to see them. So we get different print functions, but we also can visualize our tree that we have built. Because the whole chunking is, okay, you can't really see it, but you can perhaps see it on your laptop. The whole chunking is based on making an order of words that belong together. So here we still got our sentence. Artificial intelligence is artificial intelligence, AI, sometimes called machine intelligence, is intelligence demonstrated, and so on and so on. And in this tree, now you can see which parts belong together. But it's the same information we had before, it's just plotted as a nicer tree. So here we have our noun phrase with artificial intelligence and so on. But there are other ways to get an idea of which word belongs to which other word. And instead of shadow parsing, we can use a dependency parser. And for this, we use Spacy now. And normally the installation of Spacy is not really a problem, but the question is, does Spacy load the model? And if not, you have to do something, but I forgot what. So, what do we have in the end? It looks quite similar first. So our output now says artificial, and the question is, does artificial depend on any other word? The answer is no, but intelligence depends on artificial, and AI depends on intelligence. At least this is what our computer program here says right now. This is punctuation. Here intelligence, sometimes this called is intelligence sometimes is depending on called, and called depends on intelligence, and so on and so on. But we can use, here I got a second, a shorter sentence just as an example. And the dependency parsing can be done with a Stanford dependency parser as well. But if you want to, so this is taken from the NLTK library that you probably already have on your computers, but you're going to have to download these models. You have to have them local, and then just specify the path to the jar and to the models jar. If you have it, then you can get nice plots of the dependency. And the idea with dependency parsing is that you always have a root, and this is the whole sentence. And then what is the sentence all about? Oh, the sentence is about intelligence. How is intelligence now depending on other things? For example, demonstrated is depending on intelligence. Machines is depending on demonstrated. Contrast is depending on demonstrated as well. So you see, it's not, dependency parsing is not that you're going from word to word through the sentence and see what words belong together, but it's kind of deeper structure of dependency. And if it works, it's quite cool, because then you find a chunk would always be a part of words that appears together in the same order in the sentence. Dependency parsing can identify that one word that is at the end of the sentence depends on a word that is on the beginning of the sentence. So this difference.
So why is intelligence dependent on artificial? Wouldn't it be rather the other way around, that the adjective is dependent on the noun?
Here, artificial depends on intelligence.
But the first and the third, okay, wasn't it different when we did first thing? Up there?
Perhaps I just turned it around and said it wrong, but I think it works on the sentence.
Okay.
And if you take
that's fine.
another sentence, our second sentence, it's more easy to see. So the sentence was, I don't know if you saw it, a sentence about football. Bayern Munich, or FC Bayern, is a German sports club based in Munich, Bavaria, Germany. So and let's see at the dependencies here. And as always, the more complicated the sentence gets, so this is why the first sentence might not be a very good example. It's a really complicated sentence with a lot of parts in it. The more complicated the sentence gets, the worse normally the dependency parsing gets. But here it works really, really fine. We have our root, so nothing is depending from the sentence. Then it identifies club, and Munich is depending on club. And here we have two Bayern. One is Bayern München, and here we have FC Bayern. So FC is depending on Bayern. And what else do we have? This, for example, is quite cool. We have Munich depends on Germany, and Bavaria depends. Germany depends on Munich, based in Germany, and Bavaria depends on Germany. So if you follow now these dependencies, you might get some ideas about what is part of a location, or what is part of a time process, what is part of a name. So identifying names, named identity recognition is still a very big problem in natural language processing, especially if you want to find out what he, she, it in a sentence means, what is the relation of the other words in the sentence, he, she, it. This is still a very, very difficult problem. Sometimes even called a full AI problem. So if you could really solve this problem, you would need a strong AI that is able to think. Some people argue. There's even kind of Turing tests where machines are challenged to identify what was made with he, she, it in sentences. And dependency parsing is the first way to try to solve this. Why is he, she, it so difficult? For example, take the sentence 10 pictures were stolen from the museum last week. They were sold in London. We as humans understand, 10 pictures were stolen by burglars from a museum last week. They were sold in London. We understand automatically that not the burglars were sold, but the pictures. But if the next sentence would be 10 pictures were stolen by burglars from the museum, the police caught them the next day, then we know that them is not the pictures, but the burglars. So this is very easy for us, but it's very, very complicated for computers. And dependency parsing might help to solve this. Yeah, and of course, again, you can draw a nicer graph of the dependency parsing as well if you want to. So here, it's the same here before. Munich, Germany, Bavaria, but now it's smaller and nicer. yeah, the last way of parsing that is introduced here is constituency parsing, and this is something that is somehow in between dependency parsing and the POS-Tagging we did at the beginning, because as you can see here, you still have the sentence in the right order, but now you have the different connections of the sentence based on grammatical dependency structures. Okay, so much to POS-Tagging and parsing. I think I'm gonna show you first what you can do with the pattern library. There was this pattern walkthrough notebook, and here you find the address of the documentation of this library. But the documentation is really a little bit, yeah, not so good. So what can we do? For example, you got the function referenced. What you can make is you can find the right article in front of any word. For example, referenced university is a university. Referenced hour is an hour. It's not so complicated to program such a function, but it's nice to have it and you don't have to program it. Because especially when you're starting, if you want to build a chatbot in the end or something like this, it's very nice to create better sentences if you can just use these functions for text generation instead. But as you see here, the function expects a single word, so if you're entering more words to the function, you just get the output from the first word. You can also do pluralizing and singularizing, or however you call it. Yeah, child becomes children, wolves become wolf. So these are already some advanced examples, of course, because normally you can make the plural just by adding an s to a word, but there are some words that have another form of plural. And of course, this is not really machine learning in the end. This is more or less a big list of words and to know what comes next. But it even gets better. We have superlatives, comparatives that we can create from words. So bad becomes worse and worse. We have the lexeme function, which turns the whole thing around and just says, we give you the word house. What different forms of house do you know? House, houses, housing, house, for example.
For reference and superlative, if I use a reference superlative bad, would I get the worst or it wouldn't work that good?
It should work, yeah. Bad becomes worse. Yeah.
Then reference, would I get the worst?
So
if I use the reference function, would I get the worst or it only works for nouns?
Oh, well, we can try. So you mean
the reference?
Reference, worst.
like this?
Ah.
It doesn't work.
Yeah. Gives you a worst. But no, it couldn't.
For
We'll see.
only nouns.
Yeah. Yeah.
Ja.
You can alter the tenses of verbs. So here the question is the tense of period. Does it contain a P? Yeah. It contains past, so it is past tense. So we get true, true, and you can also ask, is it plural or singular? And this could be plural as well. But if you are asking, for example here, is pured present, then you get false. Run, present tense, it's true. So you can check in which tenses are words. But this function partly also works with unknown words. For example, the word to Google is not known to the library, and nevertheless Patton tries to guess the right answer. So if you're saying Google is in a verb, do we have Google in our list? It's verbs infinitives. No, we don't know Google, even not as an inflection. Nevertheless, we can use the conjugate function, but then you have to set the parameter pass on true. So this is the difference. And then you can make the conjugate of Googled, and you will get Googling as a new word. For natural text generation, the next function is really, really cool. So the function is called quantify, and now we have some words, or a list of words. We have goose, goose, duck, chicken, chicken, chicken. What do you think is the output of this function?
A lot of animals, a lot of birds.
We got several chickens, a pair of geese, and a duck. Good, isn't it? Or here, carrot with a number, parrot with 20. We have dozens of parrots and a score of parrots. Or we have hundreds of carrots. So this is really, really a nice function if you're trying to build a chatbot and you want to make the bot communicate more natural. Pattern also has, last week I showed you the spell correction algorithm of Norvig. And Pattern has introduced directly in the library is spell correction and suggestion, and with normal words it works quite nice, and the interesting thing is you get a probability what the right word might be. So if you call the function suggest and you have parrot, then probably it's a misspelling and the word was part that was meant. But if you use some more uncommon words like Hegel, then you get very strange words like feel, level, legal. The computer does not really understand what the word was, but as you can see here, the probability that the word is feel is quite low. So it's always nice in machine learning if you get a probability so that you can see how good is my estimation. Do you want to use it or not?
I want to ask, why is the probability that it is part much higher than the probability that is parrot for the parrot example?
Yeah, I don't know. So I think the algorithm they use in Pattern is based on the Nordic algorithm, but with a different text file.
Okay.
So in the end, what they are doing is
because without like the text, like thinking
Yeah.
of regular English, like in the edit distance sense, they are both the same as well.
Exactly. So let's assume they use the Nordic algorithm we introduced last week. So then this would mean parrot and part would be one string distance away from parrot, both. Here we just deleted one character, and here we just added another one. So it's the same string distance. By the way, there are many very sophisticated string distance functions. So you can have a lot of different metrics that you can use. For example, there are even functions that are taking into consideration the place on a keyboard where the characters are, because then you find misspellings from typing much more easy. So from the string distance, it's probably the same. But as we have seen in this Nordic algorithm, for auto spelling, autocorrection of spelling, you need different levels. You need a kind of algorithm that is finding alternatives, and we have now 2 alternatives, and then you have to decide which alternative to pick, and normally you have a probability model, and here the point is part is probably just so much more likely to appear in a text because there's a corpus of text, and in this corpus at least part seems to appear more often, and therefore the computer now says, I think it's part and not parrot.
Thanks.
I already talked about n-grams, and you can do this with pattern as well. So the sentence, I am eating pizza, if you make a bigram out of it, but you could just take another number here, you get I am eating pizza. So these are then your bigrams. And in classical text mining, bigrams were used a lot, and it was really an improvement to the normal just back of words approach. Because in these bigrams, now you get at least a little bit of context, the words that belong together, but as you can see, it's, I am eating pizza. These are not so meaningful like chunks, for example, might be. Yeah, the parsing we already had in the other notebook. So now here you get all the information that you have. It's, for example, here this is part of a noun phrase, this is part of a verb phrase. The last number tells you something about the relationship between the chunks. We will see this? No, we won't. A very useful function for any kind of text mining approach is you can just use pattern to extract all parts of speech, for example, all adjectives. And JJ is the code for adjectives in the pattern library. So with this function, we would get all the adjectives from a text. And especially adjectives or nouns might be very meaningful depending on what you want to do. So in, for example, we just published a paper where we try to identify what are the topics that are mentioned in Facebook posts by the different parties in Germany. And we run topic modeling in the end, so this is another algorithm that is not really connected to deep learning, but the algorithm identifies words that form a topic and finds a probability. How likely is it that one topic is appearing in a document, and on the other way, how likely is it that a word appears in a topic? So this is what these algorithms are doing. And for us, what we wanted to know what are the political issues. It was very helpful just to reduce the whole corpus and just take the nouns and nothing else. And we just did the topic modeling only on nouns. And we had much better results than if we would have taken all the words, because then words like the, and so on might form a topic of their own. So reducing information might be very meaningful sometimes. Here you see more or less all the information this pattern library has about our words. So we have I, we have a tag, PRP stands for it's a personal. We have a chunk. The chunk is a noun phrase. What role does it have? It's the subject of the sentence, and pizza is the object. And identifying subjects and objects is the key issue if you want to create a kind of knowledge graph out of natural language. Because then always what you want to find is the first thing, what is the subject, how is it connected to an object. It would be nice if it worked really well, but to be honest, it only works with very, very simple sentences.
How is it connected? Is that just identifying a verb, or is that already a meaning?
Well, this depends on you or what you would like to do, but you could of course say, okay, give me the subject of the sentence, this is I, give me the object, so we have two nodes, I and pizza, and what is the connection? It's the verb. So I eat pizza must be part of the knowledge graph. And then you could question this graph and say, what did I do? I eat, or something. But even in this very easy sentences, you see that it's probably quite demanding to make something out of this that makes sense, because then you have the problem, who is I? You have the problem, 8, what is it? Here you see, you get the lemma as well, so you could identify that 8 is past tense of eat, and so on and so on. But then you get a lot of information, and what do you want to do with it? And this is always then the problem.
Can I ask something?
Yeah, of course.
What is this ID attribute? What does it do?
It just, I think it's just the ID of the sentence. I think if you would add another sentence,
Okay.
no. What is ID?
Maybe multiple words, like multiple of the same words are used and
No. It's, I knew it, but forgot it, and I'm not online. So, but perhaps you can look at this link, and if anyone finds it out, we are all very interested to hear it. And P and B is the relation. So Patton tries to identify which chunk is depending on which other chunk, but as you can see, it doesn't really work very well. And this is a big problem with all this natural language processing tools, even the best tools, even all this Patton stuff and Spacey and the NLP package from Stanford. It's really not working very good. So normally we are used in machine learning that all the models are fantastic, and it's just the question if it's 95% or 94% accuracy. Not so in natural language processing. So there's a lot of room to build your own functions to improve all these kinds of classification stuff that is done in the background. Why did I want to show this? Ah, yes, yeah, okay. with the split function, you just can split your sentence into the chunks again. Yeah, another example. We already had this chunking in the last notebook, so it's not so important at this part. Sentence index of the last. Okay, now we try, we print the chunk string, so the chunk is the cat, the chunk role, the cat is subject, the chunk subject, so the chunk has the role that it is the subject, but if you do it like this, you won't identify in this chunk another subject. Not really intuitive, but you find that the chunk verb is sat. So the sentence is the cat sat on the mat or something like this. But as you can see for other chunks, here the mat, for example, is not identified as the object, which it should be. So the cat sat on the mat. So even these quite simple things like identifying subject, predicate, and object are not really working well, even with easy sentences. Sometimes it works, sometimes it does not work. So if anyone wants to build a really cool function that is working on complicated texts, this would be a paper for a computer science conference. And again, I think we could solve this now with deep learning, and we will try to do this in the end of the seminar, because identifying subject, predicate, and object is just a way of summarization of the sentence. So if you have an algorithm that is working in the field of summarization, we just need training samples and take a lot of sentences where we know what is subject, predicate, and object, and then we can think about machine learning ways to identify them in a better way, because all these subject, predicate, object things that we are using here now, they are based on heuristics. It's very simple heuristics, taking the structure, the dependency structure of the sentence, and then try to identify what is the subject, what is the object, and so on and so on. But language is very complicated, and therefore these simple heuristic approaches normally don't work very well, especially if the sentence gets more complicated. But this would be a nice project if you are thinking what could be a project I would like to do in this course. If you want to build a deep learning model that is able to identify subject, predicate, and object, this is really cool. Is the camera still running?
Yes.
I have a question, like it's not related to this, but more to the organizational aspect of this course.
Then
In the end.
later on.
Okay.
First, let us stick to the content. So, yeah, here we got the conjunctions. Again, this is just, there should be chunk modifiers where you can say, see what modifications of the chunk would be, but it doesn't work again in this simple sentence. We got chunk conjunctions. So this code is more or less just to show you all the different ways you could question this library. But we have the chunk PNP, where we get here on, to which chunk does on what's the dependency of on the mat. At least this. But you can also find, and this is what pattern really is about. So this now is really important. This is very cool. You can say here, go through the chunks, and now for each chunk, I want to find the nearest verb phrase. So the nearest chunk to this chunk, that is the verb phrase. And the nearest noun phrase. So our chunk is the cat. The nearest verb phrase is sat, and the nearest noun phrase is again the cat. And this might be a way to identify better what subject, predicate, and object are in the sentence. But you will see it's not so easy because often it's not the nearest chunk that includes the right object or predicate. Especially in German, you can put the predicate everywhere you want to. In the end, Yoda-like sentences. Pattern also has, and this might be interesting for some projects, already a sentiment analysis library introduced. So what is sentiment analysis? The idea is that there is a dictionary, and for each word in this dictionary you have already a value. Is it more positive or negative or neutral? And then you just run over all your text and just take the mean of your different positive or negative values. And then you can say, oh, this has a very bad, very negative sentiment or positive sentiment.
Is minus positive?
Minus is negative.
But
So I think we got it here.
I feel like the second part is more negative compared to the first part.
Let's see, sentiment function gives you a tuple for the given sentence. The first is the polarity in the sentiment function, and the second is the subjectivity. So the second, the whole text here, it's not two numbers for the two parts, but it's we get the first number is our polarity. The sentence is negatively polarized, and it's quite subjective because probably because of ridiculous and so on and so on. But these libraries are used a lot, and many, especially in marketing, everyone thinks you get very cool results with this. If you make some tests on this, you will see that it works really poorly in most cases. So it's not a very robust thing to measure the polarity or the subjectivity just based on these lexicons. But no one really cares in the end. Everyone is using it, and so you always should question the results as well. Mood refers to the use of auxiliary verbs like could or would, and the mood function returns either indicative, imperative, conditional, or subjunctive. So modality returns a degree of certainty between -1, very uncertain, and 1, very certain. So some amino acids tend to be acidic while others may be basic. And if we are running this, then we get first the modality. This seems to be certain but not really certain, and the mood is indicated. Good. The next tool I would like to introduce is the WordNet. We already had the WordNet last time because we wanted to identify different meanings of words. No, where did we use the WordNet last time in code, in the normalization code? For lemmatization. I think we used the lemmas out of the WordNet for lemmatization. But the WordNet is really, really powerful. What is the WordNet? The WordNet is a semantic lexica that was built by real linguists, and they made a graph structure. This is why it's called WordNet. It's a knowledge knowledge graph about the different dependencies of English words. And there are many ways how to connect words with each other. For example, synonyms. There are words that have the same meaning. It's a synonym. You have antonyms. You have lemmatas. You have definitions in this lexica. You have examples for the different definitions. And especially if you want to go into natural language understanding, the WordNet is probably the most powerful tool that there is on the market. And just want to demonstrate you a little bit what it can do. So we have our term. Our term is just fruit. And now we print all the synsets. So the WordNet is organized in a way. It's not really the words that are connected with each other, but you have a synset, and a synset is a semantic, is a meaning of a word. So, for example, for fruit, we have different synsets. We have the first synset called fruit N01. It has a part of speech tag. It's a noun, and it is a plant. We have definitions. The ripened reproductive body of a seed plant. This is what fruit is. No examples here, but for example, we have other synsets. Fruit is a synonym for the synset yield. An amount of a product. We have fruit. Here, fruit synset 3 is the consequence of some effort or action. So this is more like a metaphor. The fruit of your labor is nothing you could put in the mouth, probably. So we have these different synsets. And we can, for the synsets, look for entailments. Here, for example, walk entails the synset step. So this just means when I'm walking, I'm normally doing some steps. The synset eat has the entailment chew. So this is the connection between words. When I'm eating, I'm chewing. Digest means that you are consuming something. And these are very strong semantic meanings of the words that are very, very powerful. Because you can think about, for example, you found the word eat in an example, and now you know there is a very strong relation to the word chew. So if you find the one word, it might be very likely that the other word appears as well. And this could be, again, used for natural language generation. Okay.
This database is built up by hand, right?
Yeah.
So it doesn't try, if it doesn't work, no word for it.
No. So it has a lot of entries, but it's not complete, and language is evolving all the time. But it's really the best thing the linguists would do for us as computer scientists to give us this this tool, but it's not perfect and it's not complete.
Could this be a project to like estimate based on this database with deep learning what sentiments could be used in this basic sentence that we give you?
Yeah, for example, yeah. But we will see there are already some kind of implementations. For example, we're gonna try now to find what is the right meaning for a word in a given context. We're gonna touch this, but so we had entailments. Now we have definitions. For example, the word bank. There are a lot of different synsets and a lot of definitions for bank. A bank could be sloping land, could be a financial institution, a supply or stock held in reverse for the future use is the bank. A building in which the business of banking is taking place. So this is really quite interesting to see. We normally don't think about this, but there are so many words, they have so many meanings, and we normally identify the right meaning out of the context. When I'm saying I'm going into the bank, everyone knows I mean the building. But how should a computer know this? There's a project by the Allen Institute right now, and they try, I think it's a city project, but it's fascinating anyway. They try to make a database of all our everyday knowledge that we have and feed this into a computer. Because they think if we really want to understand text, we have to have all this everyday life knowledge. Like I said, I'm going into the bank, oh, this must be the building, and so on. But I think it's impossible to write all this knowledge, everyday knowledge down. And I think it's even a better idea to try it, because every day something else happens, and we have the ability to learn from our everyday experience. So a computer should somehow find a way to learn from everyday experience as well, and not we give you all the everyday experience and then you understand everything. This probably won't work, but it's a huge project. The Allen Institute is leading institute in artificial intelligence, so they are spending probably billions on building this database of everyday knowledge. Synonyms and antonyms. Very interesting. For example, large synonym. Our term is large, yeah, and then there are above average in size and number of this is the definition. And the antonym to large is small. But I'm just seeing, why is it a synonym? How does it start? We have large, then we look for the synsets. We take the first synset. Let's see. Whoops. Okay.
Multiple entries of the same one.
Exactly. So our the computer finds a synonym, but it's large. We could now print the definition and see what the difference is. But you get the idea. You can look for synonyms, and if they are specified in the synsets, then you got other words that have the same meaning, or you even find antonyms, other words that have the contradictionary meaning of the word you are looking. Same with rich. here we get it with definitions. So people who have possession and wealth, and so we have rich, a synonym to rich is rich people. The definition is people who have possession and wealth, and then there is an antonym, poor people, people without possession or wealth, considered as a group. Next step is hyponyms. What is a hyponym? If you have the word tree,
Hierarchical subclass.
exactly, a subclass. So we have trees, we have tree as a word, and then we have some hyponyms here, like Ali is a small Hawaiian tree with hard dark wood, for example. You know this, but African walnut is a tropical African timber tree with wood that resembles mahogany. So we can get subclasses of our class tree. This were hyponyms, and then of course we have hypernyms. So for example, for the sunset tree, the upper class would be a woody plant. And we even can print the whole hierarchy of these classes. For example, for tree, we have here, tree. A tree is a woody plant. A woody plant is a vascular plant. A vascular plant is a plant is an organism is a living thing. A living thing belongs to the concept whole belongs to the concept object, to the physical entity, and the physical entity is, on the highest level, an entity. And hopefully you get some ideas what you want to do with all this stuff, because I think it's really...
So entity is hyponym for everything, right?
For all the nouns, I think, at least they normally are connected to something like an entity or something like this. But in general, it's not that every possible entry is made in the WordNet. So when you're looking for an antonym, for example, and there is no antonym, and you just want to get the element, you just get an error. So if you use it later in programming, you always have to write a try function first and see if there is any element.
This database is probably most complete in English, right?
Yes, and this is the big problem, of course. To be honest, I don't know if there is anything similar in any other language. At least I didn't found it, but probably there is, because this is very widely used, and therefore I think it's quite normal that there should be, at least in German, Spanish, France, or...
I saw that the pattern library had something about web, so maybe they have different backends for different languages or
Might
different
be.
applications.
Yeah.
So there's like German, Japanese, Irish.
The German WordNet is there. Cool.
It's called German.
It's called German.
Yeah, good. And another approach would be in some weeks, 2 weeks, 3 weeks, something like this, we will touch word-to-vec vectorization, and this can be used for machine translation as well. So even if you don't have the language, but you want to use the WordNet, you could just translate your things into a vector space, compare this vector space with an English vector space, then find the most similar words and try to look up the definitions from the WordNet and then retranslate them. But of course then it really becomes high scale, and this is what Google, for example, is doing. I told you last time, I think, with this why is machine translation so biased by religious texts? Yeah, because I think I didn't. I just didn't shut it down. This was the problem, I think.
Awesome.
So it's making sounds all the time. Kommt das hin? Sieht man mich noch?
Mhm.
Gut. So, then we have holonyms. So we had hyponyms, hypernyms, and holonyms. Again, the tree. A holonym of a tree is a forest. So this means this is a broader class, a more holistic class where the other class belongs to. And meronyms this is the opposite of this. So, for example, we have still our word tree, and then we have, for example, the stump is part of the tree. A tree is part of a forest, and the stump is part of a tree.
Components.
Yeah. And you also can ask for the substance of something. So here we have, we still work with a tree. And the substance of a tree is, for example, hardwood or sapwood. These are physical substances that are part of our tree.
Does this work also as well with non-physical substance, like try to conscience, something like that? Like take the word conscience and then you try to
Okay.
find the
Let's see. You just have to see where did I specify the word. Here.
SCI.
Which word? Conscience. Like this, yeah?
This is conch.
No,
Conch.
no.
E-N-C.
E-N. Nein.
I-E.
I-E. I-E-N-C.
I.
Conscience. Yeah.
Okay. We get a definition for this. Let's see what the substance of it is. We could try the soul. What is the soul of man? Okay, but what else can we do? We have different words like tree, lion, tiger, cat, and dog. And now we can see first, okay, these are our entities. Why do we still have tree here? Word 1, 2, 3. Okay, because
Yeah.
it's the first. I just didn't see this. So we get our entities, entity names, and entity definitions. Ooh, my computer is more or less dead, so
Oh,
we don't have
that's
so
a
many
noise.
time. And what's quite cool, you can now plot all the common hypernyms of these concepts. So, for example, tree was an organism, and cat and tiger were an animal. And if you look at the next part of the notebook, the computer is dead, sorry for this. you even can measure the distance of the different concepts you have. How close are they based on hypernyms? And then you get so first we have the danke. First we have the common hypernyms. So for example, if you compare tree with tree, okay, the common hypernym is tree. But if you compare tree with lion, you find both is an organism. But if you compare lion with tiger, the closest common hypernym is both are big cats. And if you compare cat with tiger or lion, then it's a feline. If you compare dog with tiger, it's a carnivore. That is the closest connection between these two. And in addition, you can also measure the distance. So you will see that, for example, the distance between lion and tiger is 0.07, but the distance between tree and dog is 0.12. So the distance is bigger, you have to go on a higher level to get a common hypernym for these two.
What about tree and tree?
Tree and tree, the distance is 1 in this case.
Why 1?
Why? Because they don't have a common hypernym because they are from the same. It's like a cross table. It doesn't make sense to look at the diagonal in this table. So if you compare it with the plots before, you see the common hypernym of tree and tree is tree, and therefore
Biggest similarity.
yeah. I know I was just giving you the wrong numbers when I was saying this. So when you compare tree with lion, it's 0.07. But if you compare tiger with lion, it's 0.33. So the higher the number, the closer the number is to 1, the closer to the similarity. And tree has a similarity of 1 because it's identical.
I want to ask, what does this function do when, like, this also hypernym function, when you put an input that has multiple meanings?
Mm-hmm.
Does that put just like multiple hypernyms?
So we are putting here into this function already the syntax and not just the words.
Oh, okay.
So if you scroll up a little bit, you will see that these word 1, 2, 3, 4, and so on, it was already defined by a synset and not by a word. If you would just enter words, you first would have to identify the syntax. And now comes the point with multiple meanings. This is called word sense disambiguation. So you always have this problem that you have a word and you have different synsets that could match this word. What you want to do is you want to find out which is the right definition or the right synset for the word I have. And the idea is you take your sentence, the context in which your word appears, and compare this sentence with the definitions of the different synsets. And this is normally done with a LESC algorithm that is already implemented in the NLTK package. And the LESC algorithm gives you the most likely synset from all these synsets. The LESC algorithm was invented in 1986 by LESC, and from our standpoint today, it's not even it is an algorithm, but what does it do? It's really just looking for the words in the one sentence and in the other sentence, and it's just counting how many words appear in the one sentence and the other sentence. So again, this is the point where we have to say, okay, this is state-of-the-art in natural language processing, but there might be much, much better ways to solve this problem. For example, the standard LESC algorithm does not even look for synonyms or something like this. And therefore it's really good luck if it works. Many times it won't work, but again, this could be a very interesting project or part of a project. I think it's too small for a project. It could be part of a project to find better ways, perhaps again, better ways based on deep learning or at least virtual vector representations to find better ways to solve this disambiguation problem. Yeah, and this is it. This is what I wanted to show with the WordNet. We get the pattern library, we touch a lot of POS-Tagging and dependency process. And now we still have some time for questions and to talk about projects if you already have ideas. But as I said, it's not important that you already found your project and that you know what you want to do, because we still didn't touch the second big part of the seminar where it's about deep learning and how to apply machine learning algorithms.